So in this video we will talk about the spherical coordinate frame, and this is another moving coordinate frame or rotating coordinate frame that is used quite frequently in solving problems in dynamics. So we'll give an introduction to how the spherical coordinate frame is defined, how position, velocities and accelerations are generated, and we'll then get to use this in solving problems later on. So as the name suggests, spherical coordinate frame, here what we do is given a particle, let's say the particle is at a certain location in the three-dimensional space. So let's say here is our XYZ fixed reference frame, and let's say that a particle is located at a certain point. What we do is we first and let's say that the particle is at a distance r. Okay, let's say that the particle is at a distance r from the origin of that coordinate frame. So we first draw a sphere of radius r around about the origin O. So let's say that we draw a sphere of radius r about the origin, and so here is the x coordinate, this is the y coordinate, and the point P is here. What we do is, so first suppose particle, and this could be a particle, this could be a point on a rigid body, it is just a point of interest. Let's say suppose particle is at a distance r from origin O at P. Okay, so what we first do in order to define the particle in the spherical coordinate frame is draw a sphere of radius r, okay, with center at origin O. So we draw this sphere of radius r. Then what we do is, considering this sphere and the particle on that sphere, so the particle is now on the circumference of the sphere, we identify its meridian and its longitude. So I'm just using terms from geography, but it is easier when we use these terms to define the spherical coordinate frame. So let's say that this is the meridian, this is the latitude of the particle, and similarly considering the topmost point of the sphere, we then draw the meridian okay. So we draw the meridian. So this, let's say we call this L and M, and this is L. So identify the meridian M and latitude L. Okay, so we are taking terms from geometry, from geography. And we are doing this because it just helps us define the the coordinate frame. Now what we do is the way this latitude is measured is using this angle theta that OP makes with the z-axis. Okay, so we note that angle theta is a measure of the latitude. And in the spherical coordinate system, theta is measured from top of the sphere. Right, so theta is measured from the top of the sphere. So basically then the top of the sphere corresponds to 0 degree latitude, and the equator is the 90 degree latitude. So that's a subtle difference. As you can see, we use the top as the 0 degree latitude and the equator as the 90 degree latitude. Now the equatorial circle, let me draw the equatorial circle. Okay, so the equatorial circle, so this is the equatorial circle. This forms the XY plane. So in other words, the x-axis is going through this point, the y-axis is going through this point. Okay, this is just an extension of the x-axis. So the x-axis is going through this point, y-axis is going through this point. This is the equatorial circle. Of course, it forms a plane, and it actually forms the XY plane. Okay, now, and it corresponds to 90 degree latitude. We also make a note that the ZX plane forms the 0 degree meridian. So the ZX plane forms the 0 degree meridian. So this ZX plane, this plane formed by the ZX axis, that's the 0 degree meridian. Alright, and let's say that I project this point P onto the equatorial plane, and that projection happens at P prime, and I join O and P prime and extend it. Then this meridian that we have drawn from the top of the sphere through the point O, which is the meridian for this point, it makes an angle phi. Okay, and so this meridian has a measure of the angle phi. This is a phi meridian, and this is a theta latitude. So this latitude is theta latitude, and the meridian is the phi meridian, the angle phi meridian. Okay, and one thing that you can see is that if ZX forms the 0 degree meridian, then you can see that angle phi is the measure is the measure of the meridian M and in fact phi is measured counterclockwise. So phi is measured counterclockwise, CCW, from the positive x-axis. So just to go back to the figure, imagine that you have taken the 0-degree meridian plane, which is the zx plane, and you have turned it. You have turned it by an angle phi in the counterclockwise direction. So if you look at the equatorial circle from the top, okay, then turn that zx plane, which forms a meridional plane, and you turn it by an angle phi. Okay, that is the meridian of the point P, and the turn that you made is in the counterclockwise direction from the positive x-axis. Okay. We also note, by the way, and in fact we can note from here that phi dot, the angular rotation phi dot, is in the z direction. So we note that the phi dot is therefore in the z direction. Okay. Now we see over here that the angle phi is also found by just projecting the point P on the equatorial plane, on the xy plane, and then joining the points O and P prime and determining the angle that OP prime makes with respect to the x-axis, okay, in the counterclockwise direction from the positive x-axis. Okay, so we make that note here that phi is found by projecting P on the xy plane, and we denote that by P prime, and measuring the angle made by OP prime with x-axis, or actually with the positive x-axis, in the counterclockwise direction. Okay, so that's another way of interpreting phi. You can interpret it as a meridian. You can also interpret it as the angle that is made by the projection OP prime. Now let us turn our attention to the different unit vectors. So the first unit vector is found by taking this line OP and extending it in the radial direction. Okay, so that gives us the first unit vector ER. Okay, so it is a radial unit vector. So let's make a note that the radial line from O to P gives the direction of unit vector ER. Okay, and the spherical coordinate system is centered at the location of the point P. So as the point P moves, the spherical coordinate also moves, and so therefore it is translating as well as rotating. Therefore ER is radially outwards from the center of the sphere. Right? So it is directed radially outwards from the center of the sphere. The next unit vector is the unit vector that is tangential to this meridional circle. Okay, and it is like that, and we call it E theta. It is tangential to this meridional circle, and it is directed away from the north towards the south. So if I consider this to be, for instance, a sphere, and we consider the top point as the north and the bottommost point as the south, then E theta is measured. E theta is the unit vector that is tangential to this meridional line, but it is directed away from the north or the top of the sphere. So E theta is tangential to the meridional circle M, pointing from north towards south, towards S, that is north towards south, that is away from the top. Right, so that gives us the second unit vector. And if you think about it technically, since E theta is tangent to this circle, it is tangent to the sphere. So E theta is tangent to this sphere, and ER is normal to the sphere. So clearly ER and E theta are mutually perpendicular, right? So even though the diagram is sometimes difficult to interpret, but you know, if you go by the definition of ER and E theta, they are indeed perpendicular to each other. Then we make a note about E phi. We need 3 unit vectors. Now the second or the third unit vector, E phi, is going to be tangential to the latitude circle, okay, to the L circle. So since the latitude is also a circle that is being drawn on the circumference of the sphere, so E phi, being tangential to that circle, is tangential also to the sphere. So therefore E phi is also perpendicular to ER. And since we know, in, for example, in maps that we see in of the Earth, all the meridians and latitudes are mutually perpendicular to each other, right? So then E phi is also perpendicular to E theta. So therefore E theta, ER, E phi are 3 mutually perpendicular unit vectors. So E phi is tangential to the latitude circle L with a direction forming a counterclockwise circle. So the latitude, the unit vector E phi, is always going to be such that if you follow E phi, it will form this latitude circle, but in a counterclockwise manner. It'll follow that, it'll form that circle, and it's counterclockwise if you look at the circle from the top, from the north. So overall, these three vectors then form a right-handed coordinate frame. So ER, E theta, and E phi form a right-handed coordinate frame. So if you curl your fingers from R to theta, you get phi. If you go from theta to phi, you get R, and if you go from phi to R, you get theta. So that's the right-handed coordinate system, and in fact you can then see that the position of the point P, so OP, which is the position of P, is expressed using these unit vectors, is just RER. Right? So that's the position vector of this of a point which is being expressed using the spherical coordinate frame. Now we need to note that this spherical coordinate frame is a moving coordinate frame. Okay, and so in order to clarify that, what we'll do is we will show through a sketch. Let's hope that we'll get a reasonably good sketch about how the sphere in the spherical coordinate system and the meridians and the latitudes and longitudes, how they get redefined as the point moves in space. So suppose that you have this sphere, and let me draw the spheres first, because it is easier to do the drawing first of the spheres and then show the axis. So I'm going to draw another sphere with the same center O. Okay, and let's say that this was our y-axis, this is the x-axis, and this is our z-axis. Now let's say that initially a point P is located here. Alright, so in fact I'll just put the point here just for the sake of clarity, and I'll say that, well, this lies on actually, let me see if I can correct this drawing a little bit. Okay, so I just corrected my drawing a little bit. So let's say that the point P initially is located at some distance R1, let's say, and I have drawn a sphere of radius R1 and so the initial meridial, this is the initial latitude L1, and the initial meridial line goes like this. It goes okay, so that's the initial meridial line. Let's call that M. Okay, and so the initial coordinate frame is ER, like that, E phi, like this, and E theta, like that. So essentially we have the angle theta being made, the projection of P on the xy plane is P prime, and this angle is phi. Okay, so initially the location of the point is here, and it is at a distance of r1. Now assume that the point has later on moved to a location like this, okay, which is, let's say, P1, and now the meridian is going like this. It is at a distance of r, let's call this P2, so R2, this is P1, right? And let's say that its latitude is given by this larger latitude circle. So this latitude is on the larger sphere. This is M1, this is L1, and this is M2. M2 is also on the larger sphere. The larger sphere has a radius of R2. Okay, so now the ER axis goes like this. E phi is still along the latitude circle, and E theta is still along the meridial circle. And so you see, as the particle moves from this point to this point, taking some path, the spherical coordinate frame actually moves and rotates and moves in the radial direction, but also in the angular direction. And so that's why it's a moving coordinate frame. And the sphere that you draw at every instant changes if the distance of the point from the origin changes, right? So as the distance of the point P from the origin changes, whatever is the distance, you draw instantaneous sphere of that radius, and then you define the meridian and the latitude, and you find out the ER, E theta, and E phi coordinates at a given instant. So that's how the coordinate frame is a rotating coordinate frame. Now, with respect to this diagram, there are a couple of observations that we'll make. One is that phi dot rotates. Phi dot is about z-axis, and theta dot is about the E phi axis. So if you look at this particular diagram here, the theta dot, that is the rate at which the latitude is changing, that vector is going to be always along the E phi axis, and phi dot is always going to be about the z-axis. So in terms of the angular velocity of this rotating frame, the angular velocity of the rotating frame is, if you resolve these vectors, one in the z-axis and the one along the phi axis, what you would get is that the angular velocity is phi dot cosine theta ER minus phi dot sine theta E theta plus theta dot E phi. So this is basically saying that theta dot is completely in the E phi direction, phi dot is in the z direction, and if you resolve that phi dot along the ER, so you'll be doing phi dot cosine theta, and that will be resolved along the ER direction, whereas phi dot sine theta is going to be just opposite to the E theta direction. So this is my E theta, and so you have a negative phi dot sine theta E theta. So that is the coordinate, and then the angular velocity of this coordinate frame. And so what we'll do next is we will determine the expression for the velocity of the particle using this spherical coordinate frame. So if I think about the velocity is going to be d dt of RER, because the position vector of the point in the spherical coordinate frame is RER, right? So this is going to be R dot ER plus RER dot, okay? Why ER dot? Because all these individual unit vectors are all rotating in space as the point moves from one point to another. So R dot here is pretty simple. It basically says that the velocity in the R direction, ER direction, is determined by how the radius changes. Now we need to find out ER dot. Now ER dot is the rate of change of unit vector ER, which is going to be omega cross ER. Right? We have the expression for omega here. So if we carry out the cross product, ER cross ER is going to be 0. E theta cross ER, E theta cross ER is going to be negative E phi. So E theta cross ER, if you do the cross product, it's negative E phi. So you'd have phi dot sine theta E phi, and E phi cross ER. E phi cross ER is going to be the E theta direction. So you'll have plus theta dot E theta. Okay, so that's the expression for ER dot. So then we can say that therefore the velocity of the particle is given by R dot ER plus R phi dot sine theta E phi plus R theta dot E theta. Right, so that's the velocity, and to get the acceleration, you would simply have to carry out a derivative. So acceleration is equal to R double dot ER plus R dot ER dot plus, now let's take the derivative of this. So R dot phi dot sine theta E phi plus R phi double dot sine theta E phi plus R phi dot theta dot cosine theta E phi plus R phi dot sine theta E phi dot, right, plus R dot theta dot E theta plus R theta double dot E theta plus R theta dot E theta dot. So it becomes elaborate in the sense that you have all these different terms, but this is how the derivative takes shape as you differentiate these expressions with respect to time. Many a times what may happen is a certain thing certain derivative may be 0. So for example, the radius of the point may remain at a constant distance. The location of the point may remain a constant distance from O, in which case R dot R double dot become equal to 0. So you have those kind of simplifications happen. Now ER dot, as we have just pointed out above, ER dot is equal to omega cross ER, and we have the expression for that, phi dot sine theta E phi plus theta dot E theta. And similarly, E phi dot is going to be omega cross E phi, and you can easily carry out the cross product here. We have given the expression for omega in a few lines ago, or in the last page of these notes, And similarly, E theta dot is going to be omega cross E theta. And once you carry out all these cross products, you can plug them in here to get the overall expression for the acceleration of a particle when the particle's position is expressed using the spherical coordinate frame. So that is what we have in this video. It's an overview of the spherical coordinate frame, a coordinate frame that is used quite regularly in solving different types of problems in dynamics, rigid body or particle dynamics. So we'll stop here.